Okay, so today we're going to cover sections 1.3, standards and units, and sections 1.4, using and converting between units, in the textbook University Physics by Friedman and Young. Now, in the last episode, just to briefly summarize, we covered the nature of physics, and that's basically that physics is an experimental science, and we use theories to try and explain phenomena that we observe. And in sections 1.4, we simply touched on the fact that physics is hard and it requires problem-solving strategies. And most importantly, just don't give up. So let's get started with section 1.3, standards in units. Now, let's start off by discussing that experiments, they require measurements. That should be kind of clear, right? For example, if you are experimenting to try and get the velocity of your car, you would measure the distance you traveled in a certain amount of time, and that could be the distance in meters and the time in seconds, and that gets you your velocity. And if you don't really travel too far and it's not a windy day, sort of sunny, clear skies, then you could probably ignore air friction and you can ignore air resistance, and friction if it's a good road, and you get a pretty good answer. Now, we're going to define a physical quantity. Now, physics in general, you don't really need to know too many definitions. In my experience, if you're a physics major, you don't get tested on definitions, you get tested on how well you understand concepts and can apply them. But just so we know what we're talking about, a physical quantity is a number that simply describes a phenomenon quantitatively. So a number that describes a physical phenomenon quantitatively. Of course, in order for it to be a number, it has to be quantitatively. Yes, that makes sense. Okay. And the next thing that physicists need is that they need these units of measurement to be standardized. Now, what that means is that, number one, they should not change. For example, it'd be pretty weird if we defined a dollar bill to be one thing today, to be another the next year. Although it kind of does happen with inflation. But imagine it happening to seconds, where a second is one value in 2025 and it's a whole different value in 2030. Things would just go wrong. And number two is that these units of measurements should be replicatable. Now, these two things pretty much help us in making physics a scientific endeavor all throughout the world. So for example, if I'm communicating with a scientist in France, it would be extremely helpful if we used the same units of measurement, if we both used meters, if we both used kilograms, if we both use seconds, things like that. That way, we don't have to convert between our own mathematical languages if it were the case that we use different units of measurement. So this pretty much just makes it for an easy life, easy communication for scientists throughout the world. And now let's give some examples of what these units of measurements might be, which you're probably already familiar with. So we're going to cover time, we're going to cover length, and we're going to cover mass. Now, these are sort of like the base measurements that we're working with. So time, seconds, length, meters, mass, and kilograms. Now there are more units of measurements, but a lot of them are simply derived from these three. So for example, velocity is simply meters divided by seconds. Like velocity itself isn't a base unit. We take it from the ones we currently have. Moving on, let's discuss unit prefixes. Now, these are things that we add on to the word second, meter, and kilogram. Or I guess gram, kilo is already a prefix. So let's discuss unit prefixes, and we're gonna sort of take our time here. We're gonna take our time, and we are going to draw a table. And the reason I'm gonna go through this with you, it might seem kind of long, but it is good to at least do this once so that you kind of get familiar with the prefixes that are out there. And we're gonna cover quite a few right now. So let's start off with 10 to the first. This we call deca. 10 to the second we call hecto. 10 to the third we call kilo. 10 to the sixth we call mega. 10 to the ninth we call giga. 10 to the 12th we call tera. And 10 to the 15th is peta, I'm guessing, or peta. I'm not too sure. P-E-T-A. A lot of these you probably won't use too frequently, but I always just like to go through it at least once. 10 to the negative 1, that's deci. 10 to the negative 2, centi. 10 to the negative 3 is milli. 10 to the negative 6 is micro. 10 to the negative 9 is nano. 10 to the negative 12 is pico. And 10 to the negative 15 is femto. Now, I'm going to be the first to tell you, I don't have very many of these memorized. But here's the way that these prefixes work. So let's take a gram, right? Gram is your base. And for example, let's add kilogram. Now, kilogram is equal to 10 to the third gram, which is the same as 1,000 grams. That's how the prefixes work. Now, for example, 1 is a decimeter. I'm just going to use centimeter. Centimeter is more common. 1 centimeter would equal 10 to the negative 2 meters. Or, similarly, you could divide by 10 to the negative 2, and it would be the same to say that 100 centimeters is equal to 1 meter. It just depends on how you want to sort of memorize it and look at it, whichever one comes easiest to you. Now, a quick little story of the lecture video. I actually once did have to use all the way up to pico. And that was when I was working in an electrochemical lab, I guess that's what you call it. And we were working with a lot of tiny little nanoparticles. And the size of these particles were in the range of picometers. So, fun little anecdote. They do come in useful sometimes. I was always impressed because some of the lab members did know these by memory. They knew what nano was, they knew what micro was. So I would encourage you to memorize it, and I hope that one day I memorize it myself too, honestly. But moving on to section 1.4, using and converting between units. Now, the rule of thumb for section 1.4 Now, the rule of thumb for section 1.4 is pretty much dimensional consistency. Now guys, do not sleep on dimensional consistency. I can't tell you the amount of times when I was working on a complex problem, either in electrochemistry or once you get to upper division classical mechanics, like taking a course that uses Taylor's classical mechanics textbook, dimensional consistency comes in really handy. So pay attention. Don't sleep on this. It's a basic idea, but trust me, it's pretty useful. And what it is pretty much that, let's say you have an equation like let's use velocity equals distance, not over meters, over time. Dimensional consistency is telling you that the left-hand side should equal the right-hand side when it comes to units. So in our example, v equals d over t, we know that velocity is in meters over second. We know that distance is meters and time is seconds. So a quick little dimensional analysis confirms that yes, the left-hand side and the right-hand side do have the proper units. Now this comes extremely useful when you don't know the answer to things, which is what your problems are all about. You're not going to know the answer. Well, you might if you have a solution bank. But if you get to an answer on your own, and you kind of have like a rough feel of which units your answer should be in, or maybe the problem itself tells you, so it says, find the force at which the block is being pushed. You know that your answer should be in newtons, because force is in newtons. So if your answer turns out to come out, actually first let me tell you what a newton is. A newton, as you know, force equals ma. So we know that mass is in kilogram, and we either know or we will learn that acceleration is meters per second squared. So newton is a kilogram times meters per second squared. So if we were asked to find the force, we should guess that our answer is going to be in kilograms times meters per second squared. So if we get anything different, we know that we made a mistake somewhere. And that's where dimensional consistency comes to be really useful. So now let's take a second to go over some example problems. Okay, so here we are in example 1.1, and the gist of the problem is to convert 763.0 miles per hour into meters per second. Now, the way that we would do this is through unit conversion, of course. And I want to interrupt with a quick little story time. This one is hopefully funny, and it's a fun fact. So, despite some of my academic achievements in high school, like for example, in my year, my SAT score put me in the top 1% of students in the entire country. So out of 1.8 million students, I was in the top 1%, which is about the top 18,000. Despite that, what we're about to do right now was honestly one of the most challenging things I had to learn, practice, and understand near like the junior and senior year of high school and in college. Like unit conversion comes into play a lot when you're in chemistry and you're converting between like moles to whatever else you convert moles into. And I honestly struggled with that a lot. So I hope you can take that as a sort of motivation that despite someone like me who could score a pretty good result on standardized tests like the SATs, I still struggled with this very basic thing called unit conversion. And it took me about a year of like just learning chemistry, learning physics, just practicing for me to really understand what was going on. So if this sort of is daunting to you, it was daunting to me too. And let's practice and get better at it. All right, so we're going to convert miles to meters and hours to seconds. I'm going to start off with hours to seconds because it's easier. So we know that in 1 hour, there are 60 minutes. And in 60 minutes, and in 1 minute, there are 60 seconds. So as you can see, these hours are going to cancel out. The minutes are going to cancel out, and it's going to leave us with seconds at the bottom. Okay, and just as a rule of thumb, it could be good for you to memorize that 1 hour is the same as 3,600 seconds. I just spelled it out in this scenario just to take us step by step, since this is an introductory lecture. So now let's convert from miles to meters. Now, if you take a look at Appendix C of your textbook, you're going to see the following relation. That is that 1 kilometer is equal to 1,000 meters, which makes sense. But what might be new is that that is also equal to 0.6214 miles. And we care about 1 kilometer being equal to 0.6214 miles. Or in other words, dividing by 0.6214 on both sides, we get that 1 mile is equal to 1 kilometer divided by 0.6214, which is the same as 1.609 kilometers. So let's use this up here. We're going to multiply 1 mile by 1.609 kilometers. And we know that 1 kilometer is equal to 10 to the third meters. Okay. And as you can see, the miles cancel out, kilometers cancel out, and we're left with meters. So let's just see the numbers at the end of our calculation here. So it's going to be 763.0 meters per second times 1.609 times 10 to the third divided by 60 times 60. And we plug this into a calculator. I like to use Desmos on my laptop. You're going to get 341.02 meters per second. And that should match up with what you get in the textbook. So this is our final solution for example 1.1, and hopefully get a little bit more clarity as to how we convert between units. But now let's move on to example 1.2, converting volume units. Okay, so we're being asked to do two things, and one is to convert 1.84 cubic inches into cubic centimeters, and to also convert into meters cubed. Let me make some space here. Let's start with number 1. So we know that in 1 inch, there are 2.54 centimeters, or maybe we don't know, and now we do. But that's a conversion. Now, we only have 1 inch down here. We need 3. So what we're going to do is cube this conversion so that we get the proper result. And what you end up getting is that 1.84 inches cubed is equivalent to 30.2 centimeters cubed. Well, this is a rounded answer. The exact answer is a bit different, but this is rounded. Now, let's go to converting into meters cubed. And I'm actually going to use this answer because it's easier to go from centimeters to meters than it is from inches to meters. So 30.2 centimeters cubed. And we know that there's 100 centimeters in 1 meter. Remember, I either said you can either memorize it as 10 to the negative 2 meters per 1 centimeter, or 1 meter per 100 centimeters. Mathematically, it's the same thing. To me, it's just more comfortable to memorize it this way. Just makes more sense. And we're going to cube this, remember? Because we need centimeters cubed at the bottom here. Now, you don't actually have to do math for this, and let me tell you why. So you have 30.2 centimeters cubed. At the bottom here, I'm going to do some conversions. So this is basically saying 1 meter times 10 squared centimeters, and then we're cubing it, so it's the same as 1 meter cubed times 10 squared cubed centimeters cubed, which is the same as 1 meter cubed times 10 to the 6 centimeters cubed. Because remember, when you put an exponent to an exponent, you multiply the exponents. So our number up here is the same as saying 30.2 centimeters cubed times 1 meter cubed divided by 10 to the 6 centimeters cubed, which is the same as saying 30.2 times 10 to the negative 6 meters cubed. Remember, 1 divided by 10 to the 6 is the same as saying 10 to the negative 6, and that's all that happened there. So 30.2 times 10 to the negative 6 meters cubed is your final answer, but I believe the textbook phrases it a little bit differently. They use 3.02 times 10 to the negative 5 centimeter cubed, which is the same thing. It's just that the decimal was moved over one place already to the left. It went from here to here, and when you do that, you have to take one less value from the exponent. Now, that is all that we are going to cover for these two short sections, and the next sections will be sort of the final, sections 1.5 and 1.6. They're going to be the final of what I like to call the Introduction to Science part of this chapter and of pretty much the textbook. After these next two sections, which are all about uncertainty, significant figures in 1.5, then estimates and orders of magnitude in 1.6. After that, we're finally going to get to vectors in section 1.7, and we're going to pretty much be discussing vectors for the rest of the chapter. And that's really where physics begins. It begins at vectors, and vectors will be with us for a very, very long time. Definitely all the way through classical mechanics, through electrodynamics, to quantum chemistry, to quantum physics. Vectors will be with us for a while. So it will be what I like to think of as the official start of our physics journey. Right now, we're sort of just getting us up to date with how scientists think, the measurements that they use, the way that we pretty much just communicate science between ourselves. So I will see you for the next one. Later.